Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Optimization of Prestressed Precast Concrete Roof Truss by Varying its Geometric Parameters ANU-KM.Tech Structural Engineering Department of Civil Engineering Unis College of Engineering and Technology Kollam, Kerala, India SMT Kaikeyee A K Assistant Professor, Department of Civil Engineering Unis College of Engineering and Technology Kollam, India. Abstract in this paper, prestressed precast concrete roof truss is proposed as an alternative to conventional roof trusses. As the concrete is weak in resisting tensile stresses, design of roof truss using reinforced concrete is very difficult. In order to resist the high axial tension in bottom chord, the concrete truss needs to be prestressed. Here, the modeling of different configurations of prestressed precast concrete roof trusses is done using ETABS 2018 software by varying its geometric parameters such as shapes, slope, span, and spacing of the truss, and analysis and optimization is carried out to find the most effective and best prestressed precast concrete roof truss configuration suited to various conditions. Keywords: ETABS 2018, optimization, precast concrete, prestressing, roof truss, wind analysis. Introduction. In structural engineering, the title truss portrays a triangular design. A roof truss is basically a structural framework designed with single or numerous triangular units at a regular interval that comprises of straight slender members with their closes joined via nodes. The external loads conveyed by roof covering are carried out either as reactions to the walls or to the supporting stanchions. Basically, these loads are applied at the joints of the truss. In some instances, it becomes vital to apply loads at intermediate points. Correspondingly, the members are resulted to bending action besides the direct forces. Fig.1, a typical roof truss components. Steel roof trusses are most widely used type of roof trusses, but it can melt in high temperatures and can cause necking of the steel, and also steel can cause corrosion when it is exposed to marine regions. In such case, prestressed precast concrete trusses will be used as an effective alternative to it. E.Construct, an American-based company, has offered a state-of-art concrete truss girder that has been built and designed for a cement storage facility in Sharjah, UAE. Objectives. The objectives are as follows: to find out the effectiveness of prestressed precast concrete roof truss, and also to find its best truss configurations for different conditions to design the structure against dead load, live load, and wind load. To get optimum truss configuration of prestressed precast roof trusses. To validate and check the possibilities of implementation of general computer program ETABS software for roof truss analysis and design. 2. Methodology. In this study, to perform the analysis in roof truss structure, datas like shapes, dimensions, material properties, softwares which are commonly used for analysis were collected from the literature, survey and review. Models of prestressed precast concrete trusses are then designed, loads are assigned and analyzed, and optimization is done. In this study, ETABS 2018 software has been adopted to model, optimize, and analyze the prestressed precast concrete roof trusses. ETABS stands for Extended Three-Dimensional Analysis of Building System, which is a design-oriented software program specially built for the analysis of building structures. Results were evaluated and conclusions were made. 3. Modeling. Roof truss of size 12x24 m is selected for modeling with height of the column 5 m in 5 selected shapes: A-type, fan truss, Fink truss, Pratt truss, and Howe truss. An asbestos sheet M20 grade having a thickness of 6 mm is provided for roof covering. Later on, modeling was done by varying slope, 1 in 3, 1 in 4 and 1 in 5, spacing, 4 m, 6 m, and 8 m, and span, 6 m, 1 m, and 1/8 m. Here prestressed tendons are placed at the bottom chord of the truss. Material properties and details are: concrete M30 grade longitudinal bars HYSD 415 grade IJERT 10 is 060208 www.ijert.org 491, This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Tendons FE250 Grade, Tendon Jacking Stress 1120.05 N/mm2, Tendon Diameter 15 mm Table I Structural Members and its Size Member Size Columns 250 x 250 mm Truss Members 90 x 90 mm Purlin 65 x 65 mm Fig 5, How Truss Fig 2, A-Type Truss Fig 3, Fan Truss Fig 4, Fink Truss Fig 6, Pratt Truss 4. Assigned loads and boundary conditions. The following loads are assigned for the analysis of the modeled roof trusses. A dead load. It is a constant load that acts on the structure due to the self-weight of the members, the supported structure, along with enduring attachments or other accessories. The study with dead loads is considered in the building design and simultaneously in the materials unit weight. These loads are calculated as specified in IS 875-1987, Part I. B. Live load. In the case of roof truss, live load may be the load subjected by dust load, distributed, impact load and vibration, other factors such as wind, seismic, snow along with temperature variations, differential settlement, creep, shrinkage, etc. The study suggests assuming live loads in the design of buildings, for the purpose of structural safety of buildings. Live loads are calculated as per IS 875-1987, Part 2. C. Wind load. Wind motion is relative to the Earth's surface. The primary source of wind is sketched upon Earth's rotation and changes in terrestrial radiation. That further affects convection either upwards or downwards. Due to suction effect of the wind. IJERT 10 is 060208 www.ijert.org 492. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Blowing over the roof. Wind loads are usually uplifted perpendicular. Wind load is a very important factor in the design of roof truss. In this study wind parameters are calculated as per IS 875, Part 3, 2015. Table 2. Wind parameters. Basic wind speed, VB, 39 m/s, Trivandrum, probability factor or risk coefficient, K1, 1.0, for 50 years, terrain, height, and structure size factor, K2, 0.98, for terrain category 2, topography factor 1.0, for plain, K3, land, wind pressure 0.8, windward, CO efficient and 0.5, leeward, 6. Results and discussions. This section includes the figures which shows the variation of each parameters in each of the models. D. Load combinations. The corresponding load combinations between dead load, live load, and wind loads are auto-generated in ETABS software. As per the selected design code IS 875-1987, Part B, the load combinations are, A, 1.5, DL and LL, B, 1.2, DL and LL and WL plus or minus X, C, 1.2, DL and LL and WL plus or minus Y, D, 1.5, DL and WL plus or minus X, E, 1.5, DL and WL plus or minus Y, F, 0.9 DL plus 1.5 WL plus or minus X. The bottom of the column is fixed and all other joints in the roof truss are assigned as fixed. V. Analysis. Structural analysis is used to determine the effects of loads on physical structure and their components. The present study includes two different analysis, namely wind analysis and buckling analysis. Fig. 7, graph showing the maximum displacement values for all the truss models. Fig. 8, graph showing the maximum bending moment values for all the truss models. IJERT 10 is 060208 www.ijert.org 493. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 9, graph showing the maximum torsion for all the truss models. Fig 10, graph showing the maximum column load for all the truss models. Fig 11, graph showing the buckling load factor for all the truss models. IJERT 10 is 060208 www.ijert.org 494. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 12, graph showing base shear values for all the truss models. The analysis results shows that a direct proportional relation is exhibited by the displacement against slope, spacing and span. When the slope is varied from 1 in 3 to 1 in 5, displacement decreases by 56%, when spacing increases, displacement also increases by 78%, and as span increases, the maximum displacement also increases by 45%. Collating all truss types, maximum displacement is observed for models with slope 1 in 3, 6 m spacing and span 1/8 m. In the corresponding specification of maximum displacement, slope, and spacing possessed minimum to moderate range of values mentioned in the study. With this deduction, it is clearly elucidated that span is the most influential parameter, as the maximum value of span adopted in the study induced extreme status of displacement for all truss types. The parametric specification of slope 1 in 3, spacing 4 m, and span 1/2 m seemed more economical in having lesser displacement, and fan and Pratt trusses are observed as reasonable. The variations in slope doesn't induce any impact on bending moment. The maximum bending moment is experienced for slope 1 in 3, spacing 6 m, and span 6 m, whereas the minimum bending moment is experienced by model having slope 1 in 3, spacing 4 m and span 1/2 m. When spacing varied from 4 m to 8 m, bending moment increases to 72%, revealing the ideology: larger the spacing, more will be the bending. Moderate span length served as economical for the bending moment to be minimum, for plan aspect ratio 1:2. Fink truss possess comparatively lesser bending moment. Truss is subjected to torsion irrespective of the span length, rather say very negligible level of variation is induced in torsion when span length is changed. Even the maximum and minimum torsion are experienced in the same slope, that is, 1 in 3, the modifications in slope is associated with notable changes in torsion, and low slope always favored economy in terms of torsion. Torsion suffered a reduction pattern on decreasing the spacing, disclosing spacing as the most interpreting parameter for torsion. Overall, almost all types of trusses shown satisfactory result in minimum torsion except for Fink truss. The parametric specification corresponding to the boundary values of buckling load factor, BLF, shows the variation of only one parameter, that is span length, thereby indicating its dominant influence on BLF. Maximum value is attained for a span length of 6 m and for minimum, it is 1/8 m, disclosing the inverse proportionality of BLF against span length. More the span length, lesser will be the BLF. An increment of 26% of BLF had been observed on decreasing the span length. While the other two parameters remained as such for the boundary values, but spacing generally established a quite noteworthy reduction in BLF on its enhancement. Fink-type truss again observed as economical among the types of truss. The parametric specification once again divulged the modification value of span length in causing the major variation of base shear. This is the parameter of concrete truss where extraordinary deviation in magnitude had been observed. Slope modifications induce somewhat a fair variation in base shear, and a minute variation is executed with the spacing modifications. Another specialty of this parameter is that, this is the only one parameter where all types of trusses had shown similar magnitudes in maximum value. The maximum bending moment is experienced by parametric specification of slope 1 in 3, spacing 6 mm and span 6 m, and minimum bending moment is experienced with models having slope 1 in 3, spacing 6 m, and span 1/8 m. While considering the total column load, same pattern of observations and deductions as seen for the parameter base shear had repeated. 7. Conclusion: designing using steel has been the sole practice when it comes to long-spanned roofs. The ease of handling and erection, geometric flexibility, and lightweight of the steel structural components are all advantages of steel structures. But nowadays the rate of structural steel is really going high, especially in India. Nowadays cold-formed steel trusses, concrete infilled steel trusses are evolving, but concrete has not been introduced into the field of roof trusses as concrete is weak in resisting tensile stresses. In order to resist the high axial tension in bottom chord, the concrete truss needs to be pre-stressed. From the study, following conclusions was made: prestressed precast concrete roof truss can be used as an alternative to steel roof truss. It is applicable to structures which are exposed to high temperatures and also for trusses in marine areas. IJERT 10 is 060208 www.ijert.org 495. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. ETABS software is simple and convenient for the modeling and analysis of roof trusses. Optimization of roof trusses in this software appears to be very fast and easy. References: 1 Maud Azaz, Abhay Wak, and Maud Samir Ansari, Comparative Study of Trusses using STD Pro and ETABS software, International Journal of Creative Research. Thoughts, Volume 5, Issue 35, 2017, pages 70-78. 2 Sirishanai.Avalu and Dr. D. Venkateswarlu, Design of Prestressed Precast Concrete Truss and a Comparative Study with Steel Truss, International Journal for Modern Trends in Science and Technology, Volume 03, Issue 11, 2017, pages 107-118. 3 W. T. Carroll, F. W. Beaufet, and R. H. Bryan, Prestressed Concrete Trusses, ACI Journal, Volume 75, Issue 8, 1978, pages 367-373. 4 P. H. Shah and H. R. May, 1977. Precast Virendile trusses provide unique structural facade for parking structure. Precast/Prestressed Concrete Institute, Journal, Vol. 22, Number 4, pages 2439. 5 SP 38, S&T 1987 Handbook of Typified Designs of Structures with Steel Roof Trusses, with or without cranes, based on IS codes. 6's, 1893-2002, Criteria for Earthquake-Resistant Design of Structures. 7 is, 875, PART 1, 1987, Code of Practice for Design Loads. 8 is, 875, Part 3, 2015, Design Loads, Other than Earthquake, for Buildings and Structures. Code of Practice. IJERT 10 is 060208 www.ijert.org 496. This work is licensed under a Creative Commons Attribution 4.0 International License.